Thanks for the organizers for this opportunity to present our work. And today I'm going to present the work of our research laboratory from JetBrains. We are establishing some benchmarking for code, especially for long code. But as you might know, the code is always long because you have at least repository for code. So let's start our presentation. I would like to start with describing what's going on in long context and LLMs, how the relationships are there. As you might know, transformers are quadratic with respect to the sequence length, which makes them heavily on computation when it comes to processing long sequences. And you can show on this timeline what's going on. So for the year 2021, the Codex family of models were the most used one, and it was models from OpenAI, and their context window size was 4,000 tokens, which is not that long, but for models like CodeT5 or CodeBird, the context window size was even smaller. So to give you an idea of how small it is, the median for repository is around 500,000 tokens. And for a usual tokenizer, 3 characters are approximately 1 token. So here you have 12,000 characters. In year 2022, there was another popular model which is called CodeGen, with context window size of 2,000 tokens. But at this point, GPT 3.5 appeared, and the community found out that it's quite good for code, and their context window size was from 4K to 16K, which is, I'm not sure what's the exact number, because the documentation on OpenAI isn't documenting the first version of GPT 3.5. Then the code modeling became more popular with models such as StarCoder, CodeLlama, and GPT-4 as the next step for GPT 3.5. And as you can see, the context size increased to 16K for CodeLlama. And again, the problem here was that the transformers are quadratic, and you, in terms of memory and computation, so you need a lot of resources to run transformers for long context. For example, for 2 million tokens, it was almost impossible to run. But then, this field rapidly developed with these works that are highlighted on this slide. So first of all, there were some approaches to extend context window that was based on rope, rotational positional embedding. Also, flash attention is also a great step towards that, because nowadays with flash attention, the complexity is almost linear, because this multiplier of the quadratic complexity became really low. Also, there were some works on subquadratic architectures. Highlight here is Mamba model or SSN family of models, such as Hyena and so on. Also, there were some approaches that treated context differently. For example, this work on unlimiformer. Theoretically, unlimiformer allows you to have the context up to infinity. And also, this beautiful work on ring attention makes things much more easier to extend context for LLMs. But what was the problem here is that we had a lot of approaches at this time, and we tried some of them on code, trying to train with repositories, trying to train with longer contexts. but we had no data set to benchmark our results. So we could apply everything of this, and we was in the situation that we cannot understand if the quality increased or not. So we decided to work on that. We decided to develop this field because a year ago, your code benchmarks were pretty much codex glue with code completion on function level, and also human eval, which is popular now. But human eval is also a file level code completion. So what is long code arena in the end of our work? So this is a set of benchmarks, set of data sets, if you want that, which consists of 6 tasks. This is library-based code generation. I will dive into details later, but just names. CI builds repair, project level code completion, commit message generation, bug localization, and model summarization. The point here was to develop the field because human eval, for example, doesn't cover realistic programming tasks. And we aimed at this set of tasks as the representation of real-world software engineering tasks. And also, another goal of us was to start this discussion in the field because I think even until now, the discussion more or less, let's get the highest score on this benchmark. Let's get the highest score on this benchmark. But we want to develop the ideas, how can we collect data, and so on, to close the gap between classical NLP and machine learning for software engineering. Because for classical NLP, you have a lot of benchmark, you have a lot of ideas, you have a lot of data collection processes, and so on. We submitted this work to NeurIPS, and now we are in the process of making a decision from chairs. Hopefully, we will publish there, but I'm not sure. I want to present 6 tasks now. But first of all, you can check out our leaderboard. That's leaderboard on Hugging Face. There are scores there for our baselines, and there are also all the links are there, so you can check out the data sets and something like that. Or you can just Google Long Code Arena. That's name it's not taken. But you might ask why this name. This name came from the work that we were inspired by, which is Long Range Arena. That's the work from Google Research of 2020. And this work pushed the boundaries of this flash attention, SSM models, and so on. There was a set of synthetic tasks for transformers to train on and to test them, on them. So that was our inspiration. And let's dive deep into the tasks. For each task, we tried to focus on data collection process. Also, we developed some baselines, so it would be easier for users to start working with these data sets. And also, we just scratched the surface of the question of metrics, because metrics in code-related tasks are quite complicated now. And I think nobody works on that. and we would like to encourage some future research. Okay, the first task is library-based code generation. What do we do here? We start with a repository, and we extract all the elements that were defined in this project. Then we collected the files that could be considered as example files. They are usually in some directory with name examples, or they have examples name in them. So there are some filters to filter out example files. We extract unique APIs from them. And then with GPT-4 and manual verification, we generated instruction for each of the example file. Why do we need this task? Basically, we would like to follow the instruction and generate some code, some example code of a specific library. So, for example, for human eval, you don't need any knowledge of some packages, you don't need any knowledge of some libraries. And sometimes you can generate code, for example, if you use GPT-4 and you want to read CSV file, I think it generates you code with built-in CSV library in Python. But for example, you want to use pandas data frame. So we, based on these task descriptions, we asked the model to generate these example files. And here are the results. Here are the results of our baselines. The good point is that our baselines are baselines. So they're quite simple, not very sophisticated kind of stuff. So I believe the prompt here was like, generate code using this library to do this, and the instruction. Let me describe the metrics here. So we used two metrics here. The first one is href, which is a way to compare which is the way to compare how similar are the characters of ground truth and produced code. And why did we use this metric? Because there is also work that shows that this metric correlates with human judgment more than other metrics, for example, like code-bear score or something like this. Also, we used API recall as a metric, and API recall as a metric is so on the previous slide, I showed you that we extracted APIs from example files. So we extracted function calls, class constructors, and so on. And then we have, for generated code, we also have these functions and classes, and we just calculated recall. It shows us how well model can use API from the library that we have presented to it. And baselines here are now just no context, so just an instruction. Use this library, generate code to follow this instruction, and retrieved APIs, which is basically BM25 for top 20 entities. Yes. As you can see, GPT-4 without retrieval performs better than GPT-4 with some kind of retrieval. But there clearly room for improvement here. The next task I will show you briefly. So the next task is CI builds repair. Again, we started with the repository. Using GitHub Actions, we collected failed builds. And for failed builds, we collected failure logs and diff that fixes this failure log. And the task was to read failure log and suggest some patch. And we, for this task, we used GitHub. And it was not a smart choice because GitHub became outdated very quick. So the data points are not all the data points could be valid at this point, for example. And yeah, sorry. So the baseline here is basically generate some patch based on the failure log, and then push it to GitHub and check if it fixes the CI. So the scores here are not very good, but it's just based on the failure log, nothing else than a failure log. The next task is project level code completion. Code completion is quite a popular task, so we try to develop here some new approaches that then could be applied to whatever. So we again started with repository, and what we did, we traverse Git history. So we check every commit whether it has new py file added to that. If the file is added to this commit, then we use this as a completion file. And we use the repository snapshot before this commit as a possible source of context. With this approach, we try to avoid a possible data leakage when your completion file could be written after the state of repository. Also, this was one line code completion, so we need to generate one line after the prefix, no theme here. And to make the results more, to explore results more, we also introduced a classification of each line. So two main classes are in-file lines and in-project lines. There are also 5 more or 4 more classes there. So in-file line is the line that uses functions and classes that were declared in this completion file. And in-project is the line that uses functions and classes that were declared in the project, so in this thing here. And we are measuring exact match here, nothing fancy. But we are measuring it for each class individually. So here we are testing code llama. The table is quite big, so only code llama. The first row is file level context, so you have only file prefix. And for the second row, we tested different context composers. So you can compose context from the repository snapshot. Yeah, and the second line of each row is code completion with path distant context. What can we see here? We can see that, yeah, it's okay. We can see here that the on file level context in project lines completed worse, and in file are completed better. But after adding 16K of context, the results are quite similar for in file lines and in project lines. That's a result that should be quite obvious, but we need to check them. And after adding context, you can see that the overall exact match are the same as, for example, in project exact match. Yeah. So the next task is commit message generation, which is quite a classical task. So you have diff, so you have repository. We filter out large commits, which are so the minimum amount of involved files are 4,000 lines in them for these large commits. And we manually verified all the commit messages there, and we just got commits plus their commit messages. But commits here are quite huge. So the outcome of this task is that we tried different metrics here because now we are comparing texts. And metrics, the results were not very good. And another problem here is that with commit message generation, you cannot compare to ground truth because usually commit messages are quite simple, they're quite short, but model tries to make them large, tries to make them larger. So model goes into the details with this commit, and yeah, so here we have some problems with that. Problems we can not approach at this moment. Yeah. The next task is bug localization. You might know at this point about new benchmark, which is SWE bench. And actually, this is kind of the same, but we did this work concurrently with the team of SWE bench. So what we did here, we just started with the repository again. We collected issues and fixing the MPRs. We collected a repository snapshot with a reported bug. And then, after manual verification, we collected single file modifications and multi-file modifications. We started with bug fixing here, but our baselines were very bad for bug fixing. So we just, for this data set, we just used bug localization benchmarks. And the results here are the following. These two metrics are recall at 1, recall at 2. So you have your single file modification, you have your multi-file modification. This recall at 1 for single file, and recall at 2 for multi-file modification. And this is precision at 2 for multi-file modification again. As you can.
What is this 0.2 recall at 2? It's like.
Yeah, it's recall at 2. Yeah.
So why is that such a big drop?
Because we have some issues with single file modifications, which are simpler, and we have multi-file modifications, which should be more complicated.
So bug appeared after changing 2 files at once?
Yeah. So we are retrieving multiple files based on the issue, and we got this recall at 1. So we got the first retrieved file. And I think the more interesting thing here is that using TF-IDF is on the same level as using CodeBird. So just retrieving the file names based on the issue description with classical techniques are better. But of course, GPT-4, GPT-3.5 are much better at this point. And yeah. Sorry. And the last task I would like to say you about is model summarization task. This is the collection. This is data collection pipeline. So we again started with repository. We filter out documentation files, which are TXT, MD, RST files. Also, we collected referenced code from these documentation files. And we filtered out documentation that does not reference any code. And from this documentation file, we also collected doc type and intent of this documentation. So the task here is follows. We can use reference code files, and we can ask model to generate documentation with the following intent. With describing something, with giving an example, or something like this. And the interesting thing here is the metrics again, because character level metrics doesn't help us to differentiate the model results. So what we did here is that we applied LLM as a judge approach. So this metric is actually so we asked model what documentation is better for this intent. Is the first document, is the generated documentation better, or if the ground truth documentation better? And then we, okay. And here are the scores of the ratio of LLM answers that our generated documentation is better than ground truth documentation. It was also manually verified, and it shows something here. I want to also tell that the context size here matters. So if we are increasing context, then the documentation is better. But again, the problem is that model doesn't know about the size of documentation. So sometimes it generates very short documents, and sometimes it generates very detailed, long documentation, and so on. Yeah. So I described you all the tasks, all the data collection pipelines. Here you can find our email. You can write us. If you want to explore this data more, if you want to build something on that, if you want to make your own evaluation, your own baselines, and you face some problems, write us. We are open. We are answering. We're still working on this long code arena. For example, for these tasks that I present you today, the data is mostly Python, but now we are migrating to Kotlin also with our approaches. Yeah, and I just want to say that it's really important to work with code now and to find new ways to utilize code information, repository information, and everything that you work with. Because now the best solution is to treat code as text, which is not good in my opinion, but it works. So if you have any question, just reach out to us. And here our baselines. Here's our paper. You can scan them. Thank you for your attention. I will be happy to talk to you, to discuss some things, to dive into more details with you, and to help you develop this field. Thank you.
Thank you very much for the presentation. Probably I have a very naive question, but from the other side, imagine, let's say we are library developers and we want to optimize our library so it will be much more easier for LLMs to write code using our library.
Yeah.
Do you have any recommendations in terms of how structure repository, like one thing, like good examples, or it depends, like add doc strings, right? Or maybe about like API design. Like
Yeah.
It's better to have a one generic function with some flags or different functions, or do you have any insights there, like from library development perspective, how to organize it?
Okay. That's actually not a naive question.
Yeah.
That's what the community is working on right now. What I can say at this point is that that the model tends to somehow copy lines from the previous code that was seen, that was in context, and so on. So maybe if you want to generate some code based on your library, maybe you need to write a lot of tests, write a lot of examples to show how to use this, how to use that, like a lot of use cases. Because, for example, for code completion, we tried different approaches to collect context. And as I present here, the pass distance one was the better one. I believe it's because in the same directory there are similar files with similar API calls. So you need to show the model what to write, and then it can compose something from that.
Yeah, so maybe suggestion is like add not just to say unit test, but end-to-end test.
Yeah.
Bigger.
Yeah.
Okay.
Maybe to write some simple examples.
Yeah.
With all of your functionality.
Thank you very much for the talk. Can we go back to the new project code line completion slide where we have the matrix?
This one? This one?
About where we have 16K token distance.
Yeah. This one then. This one, yeah.
Yeah, about the path distance. Like, are there any way you sort the code files to have the most relevant 16K tokens, or you just go back with commit history, like how you sort it?
Yeah, actually, here we also didn't solve that. So it's an open question. We are working on this now, how to retrieve the data from your repository, which will be more relevant. We tried some naive approaches like imports first approach or declarations only approach. And the best one for us was path distance approach, which is basically sorting files based on their distance in the file tree. So the closer, so for example, files in the same directory will go closer to completion file. And files that are not in the same directory, yeah, they're in the very end of the context. And it worked better, maybe because of the pre-training. I'm not sure at this point.
And one more question about TF-IDF, where you showed it was highly compatible with Colbert. I have this assumption it works well because it is more like sparse embeddings, not dense. And if you measure exact match, you need to focus on lexical meaning rather than semantic, right? Is that right?
I think it's right. As you can see here, GTE is an embedded model. So we retrieve files based on the basically meaning of the issue. And it performs better, yeah.
You, in near future, add to your benchmark controlling models with long context at 120 frames K.
Yeah, I think we will do that at some point, but I'm not sure about the exact point.
That was my question.
You can do this and you can write your paper based on it.
We should beat their benchmarks on our own, and then they would be forced to look seriously.
Yes.
Thank you very much.